All right, so welcome everyone to the GeoQuEST seminar COVID edition. Since this is solely online, I think it's best to leave all the questions till the end of the seminar, since I don't see a raise hand function. So without further ado, as always, I'd like to start by acknowledging the traditional custodians of the land on which the University of Wollongong is situated. We pay our respect to the Aboriginal elders past and present, who are the knowledge holders and teachers. We acknowledge their continued spiritual and cultural connection to country. As we share knowledge, teaching, learning, and research within this university, we also pay respect to the knowledge embedded forever within the Aboriginal custodianship of country. Our speaker today is Alexander Francke. He is a postdoctoral at the University of Adelaide, but he's also still I believe, an honorary fellow here at UOW. His research is most heavily focused on limnology using tools from geochemistry and sedimentology. And today he will be talking to us about new proxies in limnogeology to infer quaternary landscape change. So Alex, over to you, if you want to maximize your slide.
Yeah, thanks. I hope that's all working. I might be facing a bit to the left and not always see you guys. Anyhow, yeah, so I'm actually happy to be kind of like back and present some of the research that actually got me to Australia to work with Tony over the last 3-4 years now. And obviously that was mainly focusing on new proxies to get a bit of a better understanding of how the landscape changes in the Quaternary, and in particular focusing on erosion. And I'll be talking about a bunch of projects. I will be talking quite a bit about the stuff in the Mediterranean that we've been doing, involvement by ICDP and SCOPSCO. And I mean, most people probably always wonder what the SCOPSCO stand for. It's actually Scientific Collaboration on Past Speciation Conditions in Ohrid, but it's actually also the local beer company in Macedonia. And then obviously GeoQuEST Research Center on the work both in the Mediterranean and also here in Australia. So thanks, Sean, also for acknowledgement of country. I just like to add the Ghana people, the traditional custodians of the land that I'm presenting on here in Adelaide. And then we'll mainly be talking about the Thirlmere Lakes towards the end of my talk and presentation with the Darul people as traditional custodians in that area. And I've already discussed a bit in the abstract that I circulated earlier. Why should we actually bother about quaternary landscape change, in particular in the light of climate change? We have to understand and either mitigate or adapt to these changes that are happening. In particular, one of our most important resources, which are in the end soils. In particular, if we think about the Murray-Darling Basin, the big important agricultural area. But the other thing that we're recently trying to stress a bit more is also the significance in particular of the Australian continent as carbon dioxide sink, atmospheric sink. And we don't have to go that far back in the past to actually understand the significance. Just here at the end of the Millennium Drought from 2009, coming into this extraordinary wet year in 2011, there was a very significant, in particular in the eastern parts of the country, expansion or increase in biomass production, and which actually led to a increase of 20% in the amount of carbon dioxide sequestered into the Australian landscapes, which actually had a global significance on the carbon dioxide budget. So once we got that carbon stored in biomass, it's transferred into the soils. But what happens to this carbon in subsequent drying or doing erosion and transportation? And there has been studies on that in the Murray-Darling as well, to basically assess better what actually happens with this soil carbon during erosion, transportation, eventually deposition. And obviously, if we just keep the soil the carbon in the soil, it will oxidize and the carbon is replenished back into the atmosphere. However, if we mobilize the carbon and transport it into the sedimentary sink, it's technically removed from the contemporary carbon dioxide budget. And these studies on the modern Murray-Darling actually found this probably not really surprisingly strong correlation between soil organic carbon erosion and soil erosion. However, what these authors also stressed is actually that this wasn't accounted for in the Australian National Greenhouse Gas Inventory. basically these inventories just assumed all the carbon stored in the soil is eventually remineralized and oxidized, and the carbon is replenished back into the atmosphere. And accounting for erosion as well actually reduced the amount of carbon replenished back into the atmosphere by approximately 40%. So that's a process obviously that's happening on modern timescales. But if we think about geological and quaternary timescales coming from a glacial into interglacial with associated major climatic and environmental vegetation changes, we have even less understanding of these processes, which obviously introduces a lot of uncertainty into climate model, system model, global circulation models, which are kind of the basis for our predictions of what happens in the future. So if we can't get these models in the past right, because we have these uncertainties in these models, it's kind of difficult to really precisely predict what's in the future. And currently, system and global circulation models kind of implement vegetation components and also carbon components, subsurface and above surface carbon components, but they do not account for erosion at all. So what can we actually do? There's obviously a lot of methods that we can use to quantify and reconstruct landscape response. In the past, we can do cosmogenic nuclides, work that TIBI is obviously doing on modern and paleo stream sediments, speleothem records here recorded because of the carbon isotopes we can analyze on these speleothem records. We can calculate sediment accumulation rates in alluvial or colluvial sediments. But obviously, from my own perspective as well, like lakes are actually a very ideal environmental archive because we can reconstruct the climate, we can reconstruct the vegetation history just based on our traditional proxy analysis. But until recently, it was actually pretty difficult to quantify erosion or to get a really good hand on what happens in terms of erosion in the geological past. And one method that actually allows to quantify or to infer catchment erosion from fine-grained detrital matter is the uranium isotope approach, which was first introduced by De Palo et al. 2006. And which was then taken up by Tony in particular, also in soil profiles and fluvial deposits. And the idea that Tony and I came up, I think when we met in 2014, was to really take that approach and apply it to lake sediment records where we already have a good understanding of the climate, of the vegetation history, and to bring that all together on the same archive, to not to basically infer erosion where we have a really good understanding of the climatic boundary conditions and not having to deal with uncertainties of the different archives lining up or not. So all these different methods with the Wiggle group, TIBI contributed, Tony obviously, we kind of reviewed all the different geochemical methods, also with some colleagues from the UK and France. So there's some more information on all these different archives that I've just summarized briefly, but obviously I want to talk about the uranium isotopes mostly, and I will be talking about the work I said before in the Mediterranean, then a bit of like what we did in the Mediterranean of understanding the proxy, a bit of geochemistry there to really make sure that we actually interpret the right signal and then come back to Australia. So to understand how that method works is what we actually do is looking at the activity ratio between uranium-238 and 234. So both nuclides are radioactive, decay constants of 4.5 billion and 245,000 years. And actually, because uranium-234 is a daughter nuclide of uranium-238, after approximately 4 to 5 times the half-life time of uranium-234, we expect closed systems, which is bedrock, for example, to be approximately in what is called secular equilibrium. It means the activity ratio, the number of decays between uranium-234 and 238 equals approximately 1. Yeah. To stress in a closed system, sediments, in particular loose unconsolidated sediments that we're dealing with in the Quaternary, are an open system. And if we just focus on a small detrital grain, we have some different processes happening. During the decay from uranium-238 to thorium-234, there's actually, which is an alpha decay, there is what's called a so-called recoil of this daughter nuclide thorium-234. And this recoil introduces a displacement by the daughter nuclide of approximately 30 nanometers. So if we have this closed system as bedrock or the inner part of that grain, this nuclide will just like be replaced by these 30 nanometers. But if we measure the bulk isotope composition of that grain, nothing is really changing. But if we go into the outer rim of this grain, we would basically eject this daughter nuclide into the surrounding pore fluid or into that outer rim from where the nuclide can then be leached into the pore fluid as well. So the stress is that this recoil occurs during the decay to thorium-234, but all the half-life times here are not significant on geological timescales. That's why we look at the 234 in the end. But that basically means that in fine-grained material, we increasingly lose uranium-234. And we find this depletion and these lower activity ratios in fine-grained detrital matter. I just said that. Okay, so I don't want to go too much into details how we can actually quantify then the time since this fine grain was formed. Just to give you an idea of what parameters we are working with, and what we need to understand is that this time that we can quantify between the time the bedrock was comminuted, destroyed into fine powder, and at the end present day depend obviously on the decay constant of uranium-234, on the activity ratio in the sample that we measure, then in the bedrock, the initial activity ratio, and then what's called the recoil loss factor. And this recoil loss factor in the end depends on the surface area. So the bigger the surface area of our grains are, the more actually surface we actually have to lose our uranium-234 into the surrounding pore space. So we can measure the surface area by means of gas absorption analysis, and we get a number in square meter per gram. And we need to know the recoil length, because the distance that the nuclide is replaced, the density, and then we can feed that all into our equation to calculate what was termed in the early publications Comminution Age. I will clarify that a bit more now, what this terminology is used for. So if we think about what happens in a catchment, we have our bedrock, we have a weathering horizon profile, where we actually produce a comminute bedrock and produce fine powder just at the interface between the bedrock and the weathering horizon. We will then have some storage in the weathering horizon, hill slope transportation, probably some fluvial transportation, and then final deposition. So with the help of these uranium isotopes, we can essentially quantify the entire time between comminution and present days. So since we're working in lake sediments, we can also infer the chronology of our lake sediments. So we get an idea about the age model of our sediment core. And if we account for this time since deposition, which does not, has nothing to do with catchment erosion processes, obviously. If we exclude that, we can estimate what we then started calling the so-called sediment residence time in years. And this, since it accounts for the time between formation of fine powder and final deposition in the lake basin, is a measure for catchment erosion. If we then zoom in one step further and really try to understand what happens in our weathering profile, if we have our bedrock here, the interface between the weathering horizon of soil and the bedrock. I said previously that bedrock closed system will have activity ratios somehow close to 1. We produce our fine powder here at the interface. So this is why this material close to the interface will still have activity ratios closer to 1. And since the interface between the soil or the weathering horizon and the bedrock moves downwards over time, material in the upper part of the soil profile will be stored for more time, for extended time. So this is where we increasingly lose our daughter nuclide uranium-234, and we find this trend towards decreasing activity ratios towards topsoil layers. And that's also what Tony has been working on for quite some time, to show that in various weathering and soil profiles across Australia in particular. But if we think about erosion, what then actually happens when we start mobilize our material is, if we have shallow erosion, such as, for example, sheet wash erosion, we would particularly mobilize this topsoil layer. So we will find material that is deposited in our sediment core with very low activity ratios. On the other hand, if we have deep erosion, such as gully erosion, we have activities in our sediment, or activity ratios in our sediment, which are closer to 1. Yeah. So we can also use the activity ratio as a proxy for erosion depth. So this all, like working on lake sediments on this method, mainly started with the collaboration that Tony and I started quite a while ago on lakes from the Mediterranean in Lake Doron and Lake Ohrid. This was sites that I was previously involved in doing my PhD and first postdocs in Germany. And actually, I do remember, I mean, when I came to Wollongong, I gave another talk about the paleoclimate information we can infer from Lake Ohrid. And I remember Tim saying to me afterwards, you have a lot of water there. And doing fieldwork now at Thirlmere, I finally understand or did get the point what he actually is talking about. But the site at Lake Ohrid is actually pretty important for paleoclimate in the Mediterranean, because it is, Lake Ohrid is still considered to be the oldest lake of Europe. There was a deep drilling, ICTP deep drilling in 2013. Meanwhile, we know that the lake is approximately 1.3 million years old. I will be mainly talking about the sediments from the deep core here in the central part of the lake, but only about for the late glacial to Holocene part of these cores. I just briefly want to introduce the lithology of the catchment of Lake Ohrid, just to give you a dimension. That's 30 kilometers north-south, 15 kilometers east-west. These purple color code here is particular limestones. Then we have some Devonian meta sediments, mainly silts and shales here in the northeast, tertiary conglomerates and sandstones here in the southwest, and these bluish color code are actually ophelites. And then these parts here in yellowish are fluvial to lacustrine plains, pretty flat, not much morphology. And I just would like to keep you in mind this profile here in the northeast coming through that plain into the mountain range, because we'll come back to that later. Sediment is mainly supplied here from the southeast and from the northwest, just because of the limestone geology here. There's basically no major river or creek coming into the lake from that end. So this deep drilling actually focused on the entire sediment sequence of Lake Ohrid, and early on we published the first biogeochemical sedimentary data, and that was also one reason what made me wonder, what about all the clastics in the sediment? Because the Lake Ohrid is actually a very easy system when it comes to understand the sedimentology, which is neat and nice if you want to do paleoclimate reconstruction. But in the end, we could really easily identify interglacial periods and glacial periods just by the amount of orthogenic material that is formed in the lake, such as inorganic carbon, organic carbon, biogenic silica. And that is extraordinarily high in the warmer and wetter periods. I'll come back to that in the next slides, and very low in the glacial periods. In particular here in marine isotope stage 6, basically it's very thick here against depth, which means there's very high sedimentation rates, but this all needs to come from detrital supply from the catchment, because our orthogenic matter is very low. And that's actually also, if you run those numbers, interglacials are made up to 90% of orthogenic matter, and glacials are almost 90% detrital matter. And we don't have many paleoclimate proxies as well that we can apply to purely detrital archives in terms of understanding paleoclimate and environment. So focusing now on the late glacial to Holocene record, if we really want to understand the interplay between climate, vegetation, erosion, and probably humans, we first have to do the climate reconstruction. And obviously there's been work done on Lake Ohrid for a long time. And the most important proxies that I would like to talk about is just the amount of organic carbon, which we use as a proxy for the amount of organic matter in the sediment. And just based on the ratio between organic carbon and total nitrogen, aquatic organic matter tends to have ratios of TOC/Tn below 10, terrestrial organic matter more above 10 or above 20 in that case. So we already know that most of our organic matter preserved in the sediment is of aquatic matter, aquatic origin. So we need to understand what drives fluctuations that we record here for the late glacial to Holocene record in our TOC data. Basically what we record is then the amount of primary productivity in the lake by phytoplankton, mainly Lake Ohrid and macrophytes closer to the shorelines. And that obviously depends on the amount of nutrients supplied from the catchment and then the temperature as well. So warmer, wetter temperatures promote the primary productivity, so that our organic carbon record is a proxy for temperature and runoff. And then we can start identifying our paleoclimate history. We got some warmer and wetter intervals, such as the Berlin Urariot, the early Holocene, and colder intervals such as the younger Dryas. And we also see this warming coming from the glacial into the early Holocene, into the interglacial, which is nicely mirrored here in, for comparison, the Northern Hemisphere temperatures from the ice core records in Greenland. So that's basically what we expect. But then for the mid and late Holocene, we suddenly have these low organic carbon contents, which obviously not mirror any of the climate reconstruction we infer for the Northern Hemisphere. So we have to dig deeper to understand what's happening there. And to do that, we've been looking into the amount of inorganic carbon, which is mainly of endogenic origin. What does it mean? we basically supply detrital inorganic carbon, but mainly dissolved ions such as calcium and bicarbonate into the lake. This is actually then how we chemically precipitate the calcite. So if we have dissolved ions in the lake water, the chemical equation to solid calcite crystals also requires some hydrogen, some water, and some carbon dioxide. So if we now remove the carbon dioxide because our diatoms produce photosynthesis or phytoplankton, we remove the carbon dioxide, we have to balance this chemical equation again. So to release more carbon dioxide, we also need to precipitate the calcite in the water column. So that's how we actually form the endogenic calcite. And that again depends on high spring and summer temperatures, on the supply of these dissolved ions from the catchment, and on the primary productivity. And to understand, and if we plot that downpour, we see that suddenly where our organic carbon has lower values than what we expect, the inorganic carbon pops up very high, up to 8%. And that can be translated into amount of calcite just by multiplying with 8.33 approximately, which gives us, 8 times 8 amount of calcite in the sediment. So these low calcite content or endogenic calcite concentrations in the early Holocene are still probably a bit surprising to explain. But to understand that, we have to go back to the geology of Lake Ohrid. We have the limestones here in the Galicica mountain range being intensively karstified. And even more, there's another lake here to the east of Lake Ohrid, and both lakes are actually connected through a karst system, and Lake Prespa drains through this karst system into Lake Ohrid. So the supply of dissolved calcium and bicarbonate ions basically heavily depends on the connection between these two lakes and the activity of this karst system in the Galicica mountain. And the connection, like that, the fact that Lake Prespa drains into Lake Ohrid, that sinkhole is basically just submerged by approximately 1 meter today. So if the lake level of Prespa just drops by a bit, this connection would be quickly cut off. Yeah, so that we assume here in the early Holocene and the late glacial, the karst system was not very active, and then coming into the warmer and wetter periods, the karst system became more active, and we supply more dissolved iron to the lake. And then we can probe. So basically, our orthogenic matter, organic, inorganic carbon, is both sensitive to primary productivity in some degree, and that these lower organic carbon contents are mainly dependent on dilution, mutual dilution in the sediment with these high inorganic carbon contents popping up in the mid and late Holocene. So once we got the climate story straight, the next one we need to understand is vegetation history in the catchment. There's a pollen data set published from neighboring Lake Prespa by a colleague from Cologne, Kostas Panagiotopoulos, and he also did the pollen analysis on the same side, on the deep side. Here just at a bit of a lower resolution. And what we learned from the pollen data from the previous publications, but also from the pollen data set that has been analyzed for the deep side, is that during cold and dry conditions, such as late glacial early Holocene, we have a relatively open vegetation. And in response to late glacial to early Holocene warming, we have an altitudinal upward migration of these vegetation belts. And during warm and humid conditions, we have a relatively dense woodland vegetation cover in the catchment of Lake Ohrid. And now that's basically all the information we need to start looking into our erosion proxy. We've already calculated the residence time, so erosion proxy here in the upper panel, and in the lower panel we just have our pollen data set again, which is here just simply the percentage of trees versus herbs pollen. So the higher the tree pollen percentage, obviously, the denser the woodland vegetation cover is assumed to be in the catchment, or the higher the vegetation belts have moved upward in the catchment. So what we find during the late glacial and early Holocene is that during these warmer and wetter periods, in particular during the early Holocene and during the Berlin-Aller-Road, we have relatively short sediment residence times. Coming back to what I discussed previously, indicating some deep erosion of thin soils. During the colder and drier intervals, we have longer sediment residence times, then transferring into more shallow erosion, probably of thicker soils. We just transport material from the topsoil layers that have been stored in the catchment for more extended time. But then what we also see very obviously is that if we compare the late glacial and early Holocene to the mid and late Holocene, is this massive shift towards higher, longer sediment residence times at the transition from the early to the mid Holocene. And we can obviously not explain this by climate variability. So, and this is where the vegetation cover comes in place. And you see that here, just at the end of the early Holocene, we reach these highest 3 pollen percentages in our pollen proxy in both records, in Lake Prespa and neighboring Lake Ohrid, which probably implies that the vegetation change now, like vegetation cover now, has major control and erosional processes. And if we look at this transect here in the northeastern part of the lake again, if we try to picture the lake glacial to early Holocene situation, we have some refugio woodland vegetation, in particular occurring at low altitudes, where we probably observe shallow erosion of these thicker soils developing under these denser vegetation cover. At high altitudes, however, we have very thin soils which are prone to deep erosion. So this is where we can get our climate-sensitive response to more and less rainfall that we observed during the late glacial and early Holocene. If we come into the mid-Holocene, now we have dense woodland vegetation more or less at all altitudes. And this dense woodland vegetation would then prevent the shallow erosion or the deep erosion of these thin soils at higher altitudes, and only promote or support shallow erosion of thin soils, which then means we kind of have a vegetation-induced threshold cross in the catchment-wide erosion processes from the early to the mid-Holocene transition. So now that we understand how we erode and remove our soil profiles, I just quickly want to also talk a bit about how we understand chemical weathering and soil development. And it's traditionally been done by looking into elemental ratios, comparing elements which are more mobile during chemical weathering, such as potassium and strontium, other elements being less mobile, such as titanium and rubidium. And we've been doing the same at Lake Ohrid, just ITRAX core scanning data. And we see a very distinct, significant trend towards lower titanium potassium ratios here from the early into the mid-Holocene. And we do explain that in that paper by the mobilization of potassium from the soil profiles, but then this potassium is also incorporated in secondary clay minerals, in particular in the interlayer of the phyllosilicates. Potassium can actually also absorb the organic matter and the calcium carbonates in the sediments. So this is basically using the titanium potassium ratio as a proxy for soil development. And this is also supported by organic carbon isotope data also on the same archive. And this interpretation is a bit based on a previous publication by Zanketta in 2018, who looked at inorganic carbon and organic carbon isotopes for the last 500,000 years on the Ohrid record. And in particular for the interglacials, he found this very strong positive relationship. And that in turn means if like the organic carbon and the inorganic carbon show a very similar consistent pattern across such a long time, it kind of implies that both carbon pools source their carbon for the isotopic composition from the same pool. And since we've seen before that the organic matter at the deep side is mainly of aquatic origin, that basically means that both records or both proxies respond to changes in the carbon isotope pool of the dissolved carbon in the lake water. And these authors then also discuss that this is in Lake Ohrid, in that case, mainly controlled by the supply of soil-derived carbon dioxide from the catchment. The more respiration, the more soil development we have in the catchment, the more carbon-13 depleted, carbon-12 rich dissolved carbon we transport into the lake, promoting this very low carbon isotope ratios in particular in the mid-Holocene. But then there's the question, what happens here into the late Holocene? Suddenly we see decreasing soil development, which is probably not what you expect in the course of warming and wetting of the interglacial climate conditions. So what's happening there? And to understand that, it's actually very helpful to go back to Leo Rotaka's work, a former PhD student of Tony, who has done all the work on Lake Ohrid. He has also been looking at uranium isotopes and on lithium isotopes, another proxy that Tony is heavily working on as proxy for soil development. First, if we just look at the uranium story, we see, I should have plotted that uranium isotopes the other way around, but we have the same pattern that colder and drier intervals, such as the 8.2, 4.2 and younger dryers, correspond to more shallow erosion, whereas warmer and wetter intervals correspond to deeper erosion. So we have a consistent pattern there between both sides, which is nice. And we don't see the thresholds in Doiran, which we think is the mountains surrounding Lake Doiran go much, much higher up compared to Lake Ohrid. So it's probably unlikely that the same applies at Lake Doiran, that the complete catchment was covered by dense woodland vegetation, mountains going up to 2,800 meters in the catchment of Lake Doiran. But if we look at the soil development, we have this very consistent pattern between both between both sides with very different proxies. And if you talk about any climate or environmental reconstruction in the Balkan, in the Mediterranean, during the late Holocene, you always have to consider a lot of human impact. And that is in particular something that was stressed in the paper by Leo, that this late Holocene decrease in soil development, also increasing erosion was mainly attributed to land use. And in particular, also historic evidence is that there was a very high demand for timber by Romans and Etruscans for shipbuilding, for warfare shipbuilding. So that basically a lot of slopes and mountains in the catchment of Lake Doiran, and probably the same in Lake Ohrid, were stripped from the vegetation, promoting this very deep erosion and reduction in soil development. So very intense negative feedback by human land use on the landscape in that sense. But I don't want to go too much in detail on the human impact, because I want to also spend some time on all the method development and all the geochemistry behind that method, looking into something which hasn't been used extensively in the literature. There's always questions coming up about how that proxy works, what are the limitations, what are considerations we have to do. So this work also, the first thing obviously we have to do, if we run these analysis, we want to analyze the uranium isotope composition of our detrital matter. So we need to get rid of any orthogenic stuff, organic carbon, inorganic carbon in the sediment composition. There were other methods also by Tony Slab previously published. We went back to find a bit of a faster and more effective method. And what you actually want to achieve by removing all the non-detrital matter from your bulk sediment is to see this decrease in activity ratios. Because while you lose the uranium-234 from the grain into the surrounding pore water, any material that is formed from said pore water will take up this activity ratio above 1. So organic matter, calcite, carbonates, iron oxides, any secondary matter usually characterizes with activity ratios much, much higher than 1. So by sequential leaching, we remove all these orthogenic, endogenic matter from the bulk sediment composition, and we should, with each treatment step, see this decrease in our activity ratios. So we do remove uranium absorbed to mineral surfaces, carbonates, iron oxides, and then organic matter was actually a bit of a concern for a long time, because it's actually pretty tricky to really completely and comprehensively remove organic matter from a bulk sediment composition. Hydrogen peroxide treatment is, I mean, it's long down, it's usually incomplete. So the question we had to look into again is, are there any controls by the amount of organic matter on our activity ratios, which would obviously not be erosion proxy? And this is basically the same record again. We got uranium isotopes, uranium concentrations, organic carbon, and just for orientation, I plot the calcite and calcite content here in the upper panel. And one might say, okay, I have these high activity ratios here during the early Holocene. There's also high organic carbon contents. Maybe that's all driven just by these high organic carbon contents. But if you think about it, it doesn't make a lot of sense to compare this record, the uranium isotope record, which has been analyzed on chemically treated material, to the organic carbon in the untreated material. So we had a bit of a closer look at that. And we also then measured the uranium concentration prior to any treatment in our sediment to compare that to this TOC record here in the bulk sediment composition. What you usually expect, because obviously organic matter-rich sediments usually strong reducing conditions, and uranium tends to be less mobile in reducing conditions, that organic matter is usually enriched in uranium. So many sites you find a strong positive correlation between uranium and organic matter content. We kind of find this like there's no correlation at all, which has also been described previously in the literature. And we then also looked into the comparison between the activity ratios before, after the treatment and before the treatment. It kind of implies there might be a correspondence, maybe because of these early Holocene record there. But if we look at a treated material, we actually find a strong negative correlation suddenly between our uranium concentration after treatment and TOC content. So both after treatment, which is something that just doesn't occur in nature in that sense. So that must be related to our chemical treatment. And how we explain this in that scenario is basically with that hydrogen peroxide leaching, which is oxidizing all the organic matter. Obviously, we also oxidize the uranium in that organic matter, mobilizing, removing this organic matter from our bulk sediment composition without actually attacking the triple grain, because otherwise we would see that increase in our sequential leaching steps, an increase in activity ratios in our sequential leaching steps. And if we then, what we should actually do, compare the activity ratio in our treated sediment sample against the TOC content in our treated organic matter, we see no correspondence at all, which then actually means there's indeed no control by the organic matter on our activity ratio. We also had a bit of a more look into, like, does changes in sediment supply mineralogy have any major control on our activity ratio? And with the help of Brian Jones, we did a lot of XRD on this late glacial to Holocene record from the deep side, with the idea of trying to align all the mineralogy to the different lithologies we find in the catchment. And you see that here already. That's a nice scatter plot. It's really difficult, almost impossible, to assign any clusters in these principal component analysis from these both sides, principal components between the first three principal components to any of the lithology in the catchment. And if we take the scores downpour from this PCA, from this principal component analysis, and plot that downpour, basically also to trying to find any trends and patterns in the mineralogy that might explain our activity ratio variability, we also see no correspondence at all, which then also tells us that the mineralogy does not have any major control on our activity ratio. Yeah. Then the final thing I want to talk about in terms of like geochemistry, just 2 more slides on that, is the redox conditions, basically before and after deposition. So after deposition, because there was a lot of previous work done on Lake Ohrid, a lot of rock magnetic analysis, for example, here by my colleague Jana Just, we actually had quite a few proxies that we can use to understand the redox conditions in the sediments, or just before and after deposition at the deep side. And we used in that case the ARM-SRAM ratio, which is a proxy for magnetic grain size. And not going too much into details, but fine-grained magnetite is dissolved more rapidly under anoxic conditions, which is actually picked up by this proxy. But we see this trend to more oxic conditions from the late glacial into the early Holocene, and we kind of see a correspondence to our uranium concentrations, but we don't see any correspondence to our activity ratios. And we have some scatter plots here, again, to test any statistical significance between our uranium concentration and the redox proxy, and we did find some sort of correspondence with more oxic conditions corresponding to lower uranium concentrations, which is indeed what you would expect, since uranium is a bit more mobile in oxic conditions. But that seemingly has no control. These redox conditions obviously have statistically no control on the activity ratios that we measured in the sediments of Lake Ohrid. And we also find no statistic correlation between uranium concentration and the activity ratio. And we can kind of get an idea about the amplitude, the isotopic shift we would expect for if the shift between uranium 234 238 would only be controlled by redox conditions. We can infer that by looking at the ratio between 235 and 238, and that basically tells us, comparing these two records, or the expected shift just related to redox for 238, is that these variability that we see in the Ohrid record here is 60-70 times higher than to what you would expect if it would be just like redox induced. But to take that a step further, we can actually consider the preferential mobilization of uranium-234 in more oxic conditions in our estimates for the sediment residence time. And that's also what we tried here. So the black curves here in the background are always assuming no additional control by preferential mobilization of uranium-234. And the red lines are different scenarios of leaching, preferential mobilization of uranium-234 related to leaching and not to recoil. And we, in our Monte Carlo simulations that we applied here, we assumed ratios between 1 and 1.4, and the amount of uranium totally being leached from the grain, we estimated by this equation from the literature, which basically gives us an estimate that the amount of uranium depends on the age of the sediment. And we did feed as age, we basically used the sediment residence time we calculated previously. And since there's a kind of bit of like circling argument, we also duplicated this leaching, the amount of uranium-238 being leached, just to test like an extreme scenario. And then we tested that before and after deposition separately, and we see preferential leaching after deposition does not have any significant impact. Preferential before leaching, as expected, leads to somehow lower residence times, but still within the error bar, and it would not change anything of the story I was presenting previously. Basically saying like there is a bit of an impact, but it's not significantly changing the interpretation to the story. And there's also a way to account for that, which we now also do in future studies in Australia. It is an extreme scenario, it does show some lower sediment residence times, but even in this extreme scenario, we still infer the same story that I described previously. I'm kind of checking a bit the time. I could still continue to talk about the Thirlmere Lakes, the stuff that we've done recently. I tried to keep that a bit shorter now because I spent so much time on explaining and verifying the method in that sense. So the Thirlmere Lake project is probably well known in Wollongong, mainly being driven by Tim, Sam, Tony, and colleagues from UNSW, a lot of people involved, obviously, and a lot of work done by Matt in particular in the last years. So that was very handy for the uranium isotopes, because we could just build on this existing story that already, or existing data that already existed. So Thirlmere Lakes, located just here of Wollongong, and I will mainly be focusing on this core that Matt has extensively studied before, core LC2 from Lake Kariga. Basically, just to stress that it's a very small confined catchments, and these scarps you see cropping out here in the DEM are mainly composed of the pretty weathering resistant Hawkesbury sandstone. Yeah. So Matt has also published a lot of chronological work already, a lot of luminescence dating here in black, and a lot of radiocarbon dating in red. And we see that the lower part below 3.4 meters covers the penultimate glacial and last interglacial period. Then we have a hiatus of approximately 70,000 years in a late glacial to Holocene sequence. So Matt has also previously published the complete pollen data set. And for the purpose of understanding what actually happens in terms of erosion in the catchment, also I have to say thanks a lot to Haley to explaining to me all the different pollen taxa in Australia. We went back to those which are considered significant for catchment vegetation cover only. So we got our grasses and herbs here, Asteraceae, Poaceae in the lower panel, Myrtaceae and Casuarina and Acacia in the lower panel, basically representing shrubs and trees in that context. Yeah, but what the thought was a bit to step away from just calculating the ratio between trees and herbs, which we did previously, like Ohrid, because I felt like we lose a lot of information by doing that. And we still want to compare that somehow to our erosion proxies. And that's where the idea came up, is it came to apply a PLSR, partial least square regression analysis. Probably not everyone is familiar with that, but in the first instance, what we're looking at here, it's basically essentially similar to a principal component analysis. So we feed in all our pollen taxa, and we get our positive or negative loadings on the first axis of this PLSR. And we found that we have very strong positive loadings for acacia and for our trees and shrubs, and negative loadings for our grasses and herbs. Both for the penultimate glacial, last interglacial, and for the late glacial Holocene period. So if we then take those scores again and plot that against H down core for the old time period, the last interglacial, and the current glacial to interglacial transition, we have this kind of consistent pattern of more open canopy and mid-story cover during the colder and drier intervals, and the more dense or more covered, more canopy and mid-story cover during the warmer and wetter intervals. Yeah, and this is now very handy to actually compare to our erosion proxy. And this is the benefit of a PLSR. You can start to include a response variable, which we then obviously use our residence time, our erosion proxy, to find any relationships between the vegetation and the erosion data, any statistic relationships. Yeah, and you can also, after you feed in this response variable, the residence time, you can also then model and predict the response based on the pollen data. And that's basically what I'm showing here. So on the top panel, we just have the measurement, the activity ratios, and then calculated sediment residence time. And in the lower panel, we basically have the erosion predicted or modeled based on this vegetation data input. And we see a very consistent pattern between less erosion, longer sediment residence time during warmer and wetter intervals, and more erosion, faster erosion during these colder and drier intervals. So a very strong correspondence between vegetation cover in that sense and the catchment erosion. We don't see, like, there's a bit of this part here, which is just on top of the hiatus. There's no pollen in that interval because it's highly oxidized. The interpretation why we have this long sediment residence time, which we cannot really explain with the vegetation data, is basically that we have this like 70, 80,000 year long lasting hiatus where erosional process and sedimentary processes were probably very slow in the Thirlmere catchment. So when conditions became a bit wetter, more humid again, we start to mobilize this material has potentially been stored in the catchment for a very extended time and wash this relatively old material into the lake basin before we then start again with our relationship between the erosion proxy and the vegetation cover. Yeah. And the next step, bringing us back, what I actually tried to stress at the beginning of the talk is like, what does it mean for the amount of organic carbon being mobilized and transported from the catchment into the soil? So I think it was Matt and Bryce actually went out and dig this 50 centimeter deep soil pit, where we also took samples to measure our uranium isotope proxy, and we kind of see this expected trend, what's the lower activity ratios in the soil profile, and also probably not a big surprise with more soil organic carbon in the topsoil layers, which then means if we have shallower erosion in the topsoil layers, we would mobilize material that has been stored in the catchment for longer and potentially some more soil organic carbon from the topsoil layers. During cold and dry intervals, where we have some deeper erosion, we would also start mobilizing material from deeper parts of the soil horizon and more degraded soil organic carbon and soil horizons with lower soil organic carbon contents. Yeah. So if we try and just briefly bring that together in terms of like what happens with the interplay between biomass production, vegetation cover, and erosion. During interglacials, we have high biomass production in the catchment as inferred from our vegetation reconstruction, more trees, more shrubs producing a lot of biomass in the catchment. During this time, we've preferred mobilization of this organic matter-rich topsoil layer, and before you can mobilize that, you probably also mobilize a lot of loose leaf litter. Yeah. And during the glacials, basically have less biomass production, but also deeper erosion in that context. We, like, together with Brad Pillans from ANU, we've also been starting to work on Lake George. I just want to show this last slide on that topic. On a preliminary chronology, I should say, we also have the activity ratios at that stage for the Lake George record, and for the late glacial to Holocene, we see a very consistent pattern coming from some deeper and faster erosion into slower and shallower erosion in the warmer and wetter interval. And I found that very interesting that despite the settings at Lake George, obviously a much bigger lake, that we get such a similar and consistent signal from the uranium isotopes between these different sites. We're probably the same similar-ish climate and environmental conditions, but the site-specific settings, the geology, the geomorphology, the catchment size are very different. So just to summarize that on Australia, interglacials with high terrestrial biomass production and slow and shallow erosion, probably mobilization of weak decomposed topsoil and organic matter leaf litter. During the glacials, I basically just said that before, with low terrestrial biomass production and fast and deeper erosion. In terms of the uranium isotopes in general, we've shown that it's a new analytical tool to kind of quantify erosion from fine-grained sedimentary archives. With all this work, in particular, we did in the Mediterranean, we kind of became much more confident, I believe, that uranium isotopes remain controlled by catchment processes and erosion. And we also see at all the different sites, it's actually a very complex interplay between erosion, climate, vegetation, and then also humans, which I haven't stressed too much today. In the future, obviously, we need to test if this is all just like regional, local signals, or is it actually a regional information that we're seeing there? There's a lot more we can do with the vegetation data that like has in the last years coming up more and more in Australia and been presented at Aqua, would love to do that. And then to basically get a better understanding, better hold of these this interplay between soil organic carbon and cycling and erosion, focusing a bit more like on organic geochemical data that we can apply for the lake sediment record as well to assess the degree of degradation of material of organic carbon coming from the catchment into the lake and the contributions from the catchment versus contribution from like aquatic or semi-aquatic biomass production in the lake. So there's more to do. Just to acknowledge for all the work on Lake Ohrid, the Skopsko community, then obviously Tony and the Wollongong Isotope GeoQuEST laboratory, and then in particular Tim and Matt and Brad for the work at Thirlmere. But obviously there's much more names to say on the Thirlmere project. Sam is involved, Scott Mooney and Hayley were in particular helpful with the pollen data. But with that, I think I'm a bit over time already. Thanks everyone for the attention.
All right, thank you very much, Alex. We now have some time for discussions. So in the interest of not talking over each other, maybe if you have a question, just say so in chat and I will call on your name.
Okay, apparently we do have a question here in the map library from Andrea.
All right,
She's
go ahead.
walking up now to ask it.
Can you hear me?
Yeah.
Thank you. Thank you for your talk. I understood maybe a teeny bit of it. I'm curious about grain size. You up with the uranium. You talked about surface area and volume and density. Did you also have to consider grain size, particle size?
So we did that for the Lake Ohrid record as well. Like we have some grain size data there, and we tested it in the early days already if there's any correspondence between grain size and the activity ratio. So there's no correlation on that end, but grain size and the surface area would also be tied very closely. So if you have a larger grain size, usually the surface area would tend to decrease. So basically by including or accounting for the surface area in our calculations, we also do account for changes in grain size. But I should also say that I didn't mention it previously, that we do see before we do our analysis the samples to 63 microns to really just focus on the fine material, on the fine powder.
Thanks, Alex.
All right, Alex, I actually have a follow-up question on that because you mentioned that the activity ratio is fairly constant in bedrock, but it's less than 1 in smaller grain sizes. I was wondering, does that ratio change over time as well, assuming the grain size stays the same?
Yeah, I mean, so the first thing that happens when you have the fine powder, you lose, if we're talking about the fine grains, we're talking about the bedrock.
Just the fine grains.
Yeah.
Because
so
I assume as you, I assume as you eject more of the radioactive isotopes out from the surface, you would continually lose the activity.
Yes. So, but that's basically why you start to like see these lower values, these lower ratios in the fine powder over time. It basically gets to a point where at some point you probably would have lost theoretically all the uranium-234 from the outer rim, from the outer part of the grain, and that's where you would like not lose. Obviously, you can't lose any more 234, and that's also kind of like one limitation of the method. You couldn't apply it to sediments which are usually which are way too old, where you have lost all your 234. And at some point you will also start to gain more uranium-234 by the decay of 238 into 234. Yeah. But since the half-life time of uranium-238 is very long, I mean, we've been applying method now, obviously, for Thirlmere back to late stage 6. We also got data to early stage 6, and that's like still works fine there. If it goes way beyond, then you have to consider the decay and not just the recall as well. So then it gets a bit tricky there.
Right, thank you. Does anyone else have any questions? Feel free to just unmute your mic and ask. All right, well, it looks like we don't have any more questions. Maybe your talk was just too comprehensive. So I will end the recording here, but I will keep this room open in case anyone wants to just talk to Alex and talk amongst yourselves. But thank you everyone for coming to this seminar. We have another seminar next week on Wednesday from Dr. Colin Woodruff. So we have that to look forward to. Thank you again, everyone.